All right, so picking up where we left off, we're going to talk just briefly about the structure of the periodic table and how we can use that to help us with our studies. So once chemists began exploring the different types of elements, they noted that while each element has its unique properties, there are specific traits and trends that were reoccurring. So the periodic table is what was developed by the Russian chemist Dmitry Mendeleev as a way to group and categorize the elements by those characteristics. Now here we have just a very small portion of the periodic table, but it's going to have all of the significant atoms that we're going to be discussing in this course. If you go on to take a chemistry course, you will be using a full periodic table, but for our purposes, this will be sufficient. So this is just going to be a small portion to help us understand how it's organized. Atoms of an element are going to be arranged horizontally by an increasing atomic number in rows called periods. So this very first period has hydrogen and helium, and you can see that they have one or two protons. This number right up here is our atomic number, and that's going to tell us how many protons are going to be found in that particular atom. So they're going to be arranged horizontally by increasing atomic number in rows called periods. Atoms of an element arranged in vertical columns are going to be called groups. Atoms with the same group share similar characteristics. Most importantly, they share the type of chemical bonds that they form. So for example, over here, we have what is known as group 8. Group 8, all of the atoms that are found over here, or elements that are found over here in group 8, these are called noble gases, and they're inert, meaning that they are very rarely ever going to react with other atoms. So helium, neon, argon, krypton, they are all examples of noble gases. Atoms that are found in the periodic table are shown as electrically neutral, meaning that if their atomic number of neon is 10, we have 10 protons. So if we have 10 positive charges, we're going to need an equal number of negative charges. So how many electrons does that mean that we're going to have? 10, very good. It's a little bit weird doing this as a video without getting your reactions and your responses, but if I ask questions, please feel free to pause the videos and see if you can answer them before I continue. This will help you help you see if you are really understanding the material as we go along. So, atoms shown in the periodic table are electrically neutral. So the atomic number is also going to tell you the number of electrons as well as the number of protons found in any particular atom. So it's not possible to determine the precise location of an individual electron at any given moment. So we must have a model to approximate where electrons are going to be distributed. What you see here is a Bohr model. This is one of the more common models developed by the physicist Niels Bohr. In this model, the electron shells are about the nucleus. These are going to be used to represent the average energy levels of an electron. So the negatively charged electrons are attracted to the positively charged nucleus. It's going to take energy to push them away and keep them out in their own energy shells. The more distant, I've got the hiccups. The more distant the shell, the more energy that it has, or the more energy it takes to hold it out there. Thus we describe electrons as being at a particular energy level in relation to the nucleus. So we're going to talk about this quite a bit when we get into photosynthesis. We're going to talk about electrons jumping from one energy shell to the next energy shell, or getting so excited that they actually fly off the outermost energy shell and can leave the atom completely. So this electron, and based on its location, this energy of the electron based on its location is going to be very important. So electrons have energy due to their relative positions. This is what's known as potential energy. Electrons can then move from one energy level to another. So like I said, in the process of photosynthesis, when atoms absorb the energy of the sun, electrons are going to be boosted to higher energy shells based on this energy transfer. And as they return to their original energy level, their energy is going to release and they're going to transfer it to a form of chemical energy, namely glucose. So one of the things that we want to discuss is going to be the distribution of those electrons. So for atoms with an atomic number of 20 or less, the following rules are going to apply. The very first energy shell can hold up to 2 electrons. Each additional energy shell can hold up to 8 electrons, and each lower shell is going to need to be filled before the electrons are placed into the next energy shell. So when we're determining how we're going to draw our atom, our atom is always going to be drawn with our protons and neutrons inside of the nucleus, and then we are going to arrange our electrons based on these rules, with the first energy shell holding up to 2 electrons, each additional shell holding 8 electrons. So let's use this as an example to try and draw the molecule of sulfur. So here we have sulfur. It has an atomic number of 16. So that atomic number means that it has how many protons inside of its nucleus? 16, very good. If it has 16 protons in the nucleus, that means it has 16 positive charges in the nucleus. If it is an electrically neutral atom, if we have 6 protons, how many electrons will we have? 16, very good. We will have 16 total electrons. We need to have 16 negative charges to balance out the 16 positive charges. So now if we're going to draw our atom of sulfur, we're going to start off by drawing our nucleus. We'll put all of our protons and neutrons inside of our nucleus, and then we're going to put 2 electrons in the first energy shell. That first energy shell can hold up to 2 electrons. Each energy shell after that can hold up to 8. So how many electrons will go into this next energy shell? 1, 2, 3, 4, 5, 6, 7, 8 electrons. That is the max that can be held. How many electrons are going to go in the outermost shell? Well, how many electrons do we have left? We put 2 in the first one, we put 8 in the next one, so that's a total of 10. How many electrons do we have left? 6. We have 6 left, and we can put up to 8 in each energy shell. So we're going to put 1, 2, 3, 4, 5, 6 electrons in the outermost shell. So I strongly recommend that you take some time to practice drawing electrons. When we meet in person, if we get together, I would love to go over this with you guys. I do think it's a very important part of this semester that you are able to draw a model of an atom and understand its placement, understand how the positive and negative charges balance out, and understand the location of electrons. This is going to play such a very important role once we start bonding our electrons to form molecules. So we've talked about the structure of the electron, but what I want to focus on now for just a moment is going to be specifically the valence electrons. So the outermost shell of any atom is what we call the valence shell. This is ultimately what's going to be responsible for determining the properties of that atom. So I know we talked about how the protons determine the properties of the atom, and they do. Those protons also determine the number of electrons, and those electrons in this outermost shell are going to determine its reactivity, or how that atom is going to respond to the other atoms around it. So one of the things that we're going to start off, or I just want to give you guys, is the octet rule. The octet rule states that the valence shell will be most stable when it is full. And as we said before, the first energy shell can hold up to 2 electrons. Each energy shell after that can hold up to 8 electrons. So in other words, when we have a completely full energy shell, the atom is stable and it's not going to be terribly reactive. Now, if you remember, when we talked about the periodic table, we talked about this section over here. We talked about how in this group over here, we have our group 8 atoms, and these are going to be our noble gases. All of the atoms in group 8 of the periodic table have 8 electrons in their valence shell. So, will this group be reactive or stable? They're going to be really stable. They have a completely full outer shell. They don't want to react with anybody else. Each atom in a group has the same number of electrons in its valence shell. The number of electrons in an atom's valence shell ultimately determines whether that atom is going to give up, accept, or share its electrons to acquire 8 electrons in that outermost shell. So, for example, over here we have our group 1, or we have our group 1 atoms. So all of the electrons, or all of the atoms over here, have 1 electron in their outermost shell. They want to have 8. And so having only 1 electron in their outermost shell is going to change how it reacts. They are going to be very reactive with anyone over here. Over here in group 7, all of these individuals have 7 electrons in their outermost shell. They want 8. So there is a very good chance that you're going to see group 1 atoms hooking up with group 7 atoms, because they're going to want to have a full and complete balanced energy shell, valence shell. So atoms that have their valence shells filled with electrons tend to be chemically stable. Atoms that do not have their valence shells filled with electrons are chemically reactive. And like we said before, these individuals over here, well, not these atoms over here, are going to be our group 8 atoms. They have 8 electrons in their outermost shell, and they are going to be chemically inert, meaning very unreactive. It's going to take a lot of work to get them to react. Here's why we care about reactivity. Molecules and compounds are formed through the activity and reactivity of the outermost valence shells. A molecule is going to be 2 or more atoms bound together, and it's going to be the smallest part of a particular compound that retains its chemical properties. You may also see the term compound being used. A compound is a molecule containing at least 2 different elements. So, for example, oxygen, hydrogen or oxygen gas, or hydrogen dioxide, or H2O, dihydrogen monoxide, has 2 atoms of hydrogen and 1 atom of oxygen. A compound is going to be specifically molecules that are made up of different atoms. So in this case, water is considered a compound. Oxygen is not a compound. For our purposes, we're going to use the term molecule. It's kind of like how all squares are rectangles, not all rectangles are squares. All compounds are molecules, not all molecules are compounds. So we're going to just use the term molecule, but in case you see that, your textbook does take the time to explain the difference, so I thought I would mention it. So in biology, we tend to use the term molecule. So for example, this is going to, I don't have it listed here, but the molecular formula for glucose is going to be C6H12O6. The letters are going to indicate the types of elements that are present in the molecule, and the subscripts indicate the number of each atom present. So in the case of water, we have 2 hydrogens and 1 oxygen. Electrons are going to possess energy, as do the bonds between atoms. Organisms are directly dependent on chemical bond energy to help maintain their organization. And as we'll learn later this semester, organisms routinely break down glucose to obtain energy. This energy is obtained when the electrons shift. They shift to change their relationship from one atom to another. We're going to look specifically at this shift in energy relationships known as chemical bonding. Specifically, we're going to be focusing on ionic and covalent bonds. All right, I'm going to pause here, and we are going to pick up in our next video with ionic and covalent bonding.